Good evening. So we are most fortunate to have Dr. David Montgomery with us tonight from the Earth and Space Sciences program at the University of Washington. So let's give Dave a evergreen welcome. Thanks for coming, Dave.
Sure. Well, thank you. Other than the traffic on the drive on the way down here, I'm glad to be here. But I'm going to talk to you tonight about the series of 3 books that my wife and I jokingly call our Dirt Trilogy. If you'd asked me 10 years ago, when I first started writing that Dirt book that I understand a few of you may have read, I would have told you that you were crazy if you had asserted that 10 years later I would be standing in front of people talking about not 1, but 3 books that I'd written about soil. So part of my job tonight is to try and explain to you why a geologist like myself, because I'm not a soil scientist, I'm not a farmer, I'm not an agronomist, I'm a geologist. I trained to study how landscapes evolve. I want to explain to you why somebody like me would actually not only think that soils are fascinating and interesting, but worth actually devoting a substantial amount of time to studying and thinking about and looking at the relationships between human societies and the skin of the earth, the part of the earth that covers up the rocks I was trained to study. And this series of books, that first one, Dirt, talks about the role of how people treated land in ancient civilizations, how that affected the longevity and durability of those civilizations. And there's a simple message there. Societies that didn't take care of the land did not take care of the people. That's also the book that you might expect a geologist to write, because it's backwards looking. It's looking back through history, kind of the way I was trained to do, but just looking at the very most recent part of geological time, the part that we've been influencing. That middle book, The Hidden Half of Nature, that I wrote with my wife, a biologist, Anne Baclay, talks about how we restored life to the soils in our yard. And I'll give you a little more detail on that book as well. But I'm going to mostly focus on the first and the third books tonight. And that third one over on the right takes some of the lessons that we learned really in our own yard and tries to apply them around the world to look at the problem of really restoring health and fertility to the world's agricultural soils. It's something that I actually think is one of the biggest natural infrastructure projects that humanity faces. And part of my job tonight is to try and tell you this full story, but also take you on a journey that will probably depress you at the start. And if you've read the Dirt book, you're acquainted with some of the arguments there. But by the end of it, I want to convince you that we can actually turn the problem that I wrote about in Dirt around. And so in part, this is sort of a discussion and a walk through my journey going from sort of a deep green pessimist about the future of our ability to feed the world to somebody who's actually genuinely optimistic that we can solve the problem of soil degradation. Now, you wouldn't get that from this map. This map is the UN's global map of soil degradation, and it shows you, as of a few years ago, areas that they defined as degraded or very degraded in terms of the land's ability to feed people, its agricultural potential. We've actually already degraded a substantial amount of the world's topsoil that we inherited at the end of the last ice age. And this map puts that in perspective. This is a global problem. But the part that you can't tell from this map is that within each of those red zones, within each of those areas of very degraded soil, you can go find farms where the farmers are using intensive agriculture to rebuild the health and fertility of their land, completely turning around the broad pattern that you would get from the global perspective. That's what I want to talk about tonight. That's what I want to basically share with you, both the history and background, the insights into how recent developments in science are coming to point to methods that we can use to improve land as we intensively farm it, and then take you to visit some farmers around the world who've already done it. It's not just a theory that you can restore fertility to land. This is something that actually has a very strong evidentiary basis. You wouldn't get that from this map. You also wouldn't get it if you just looked at the total magnitude of soil degradation that's sort of culminated in the later part of the 20th century. Because between the years after the Second World War up to 1995, when David Pimentel and his colleagues at Cornell wrote a fairly influential paper looking at the state of the world's soils, they basically summarized that at that point we'd abandoned some 430 million hectares of farmland around the world. That's an area the size of China and India combined that had been lost to agricultural production as a direct result of soil loss and soil degradation. Any way you look at the problem of how to feed the world in the future, it'd be a lot easier if we still had that 1/3 of global cropland still at its full native productive potential. Yet that rarely gets discussed in terms of the broader problem of feeding the world. Now, what's the current state? This is the most recent assessment I can find. It's again from a UN document, the Global State of the Soil Assessment from 2015. And it reported that humanity is losing another 0.3% of our global agricultural production capacity each and every year due to ongoing soil degradation and loss. Now, 0.3% sounds like a pretty small number, doesn't it? Unless you start thinking like a geologist and go, oh, well, what's going to happen at that pace over the next 100 years, over the next century? And if you play that out in your mind, we're going to lose another third at the pace we're on now, another third of our agricultural productive capacity. And this is a fairly conservative estimate at current rates. There was another study a few years ago that projected we only had 60 years of topsoil left. I think that was a little alarmist. But to a geologist, if we burn through another third of our agricultural productive capacity in the next 100 years, that's plenty fast. And think about that. If we manage to do this, we will have, by the end of this century, degraded 2/3 of the capacity of the Earth to feed people, all at a time when our population is expected to go up by another 50%. That's not a terribly good planetary management strategy, however you look at it. So it's my contention that agriculture is going to have to change in the next century. The trick is how. And I also want to basically start, well, that's where I want to get to. And I've already advertised that I've turned into an optimist on this issue. So I hope that you kind of sense where I'm going with it. But first, I'm going to take you down a deep well of depression. Because we're going to look back at the history of how ancient societies have treated their land. Not all ancient societies, but the vast majority of them that I can find in the historical record. And that's what I wrote about in the Dirt book. Basically looking at the archaeological record, going to places and digging holes, looking at the nature of the soil in places, and piecing together historical accounts to look at how people treated their land and what that in the end did to those civilizations. And what you basically find is that soil erosion, in one form or another, helped bring about the demise, it played a role in the demise of ancient civilizations, going from Bronze Age Europe, Neolithic Europe, Rome, classical Greece, Mesopotamia, the southern United States, which one we don't tend to teach in history classes, but I wrote a whole chapter on, basically, and Central America, societies around the world. You can show to the archaeological and geomorphological and geological record that soil erosion actually was a contributing factor to their demise. Now, what you tend to find in environmental history textbooks is that the proximal cause was deforestation. That's the sort of one-sentence explanation you'll find in most popular treatments and in most environmental history textbooks. And I've actually worked on soil erosion in the Northwest and landsliding, some fairly controversial cases in the last few decades, looking at the role of landsliding on soil erosion in the Northwest. And I can say two things with absolute certainty about that. One, clear-cutting steep slopes increases the rate of landsliding. There's no room to debate that, and there hasn't been since the Mycenaean time. Second, you can't explain through deforestation the wholesale loss of soil off of regions of the ancient world that I'll show you in a few minutes, because the susceptibility to increased landsliding as a result of deforestation or timber harvest, whichever you want to call it, is actually a very small part of the landscape. The numbers simply don't pencil out to point the finger at deforestation to explain the loss of soil in ancient societies. This led me to the conclusion that there was actually a very different villain in ancient history that actually has a lesson for us in terms of agriculture today, because that villain, if a nonfiction book can have a villain, the villain of the Dirt book is the plow. Now, why? Well, if you've read it, you know the answer. Because plowing the soil, tilling the soil, while it is actually exceptionally good for weed control, if you invert the earth, you're leaving the land surface bare and vulnerable to erosion by wind or rain. That's a fundamental change in the nature of the surface of the earth. How many places have you gone out to that have our natural grassland or natural forest where you see a whole lot of bare earth, unless you go above the timberline or you go to Antarctica or something? No, nature clothes herself in plants. And there's very strong reasons for that, or very strong connections why that was very successful in terms of plants colonizing the continents. A covering of plants will help protect the soil from erosion, and if the soil is protected from erosion, all that organic matter that the plants are producing when it dies, and all things ultimately end up dying, that can get reincorporated into the soil, make the soil more fertile so you can grow more plants. There's connections there, positive feedbacks. The plow essentially undoes that. How big a deal is it? Well, I'll show you some pictures in a minute, but I'll just share a fun fact. Anybody care to guess where that image is actually from and what it is of? And no, it is not space aliens following llamas, which is kind of what it looks like, right? It's from Mesopotamia. It's the very first image that we have of a plow. It's from about 4000 BC, if I'm remembering the numbers right. And by way of caveat, if I present dates and so forth, trust the book, don't trust my memory. That's why you write stuff down. But it's from thousands of years ago in Mesopotamia. It's from a cylinder seal. It's about the size of my index finger, and it's from rolled baked clay. But this is plowing tillage goes back a long way. And there are those who have argued that the plow has done far more damage to the world than the sword. And think about that when we're taught to turn swords into plowshares. The damage that plowshares have done to the world's landscapes around the world has actually been very unappreciated through much of history. We can go to our own state of Washington, to eastern Washington, for a really good example of why a geologist like me would look at tillage or plow-based farming as something that causes soil to simply bleed off the landscape. This is a picture of a winter wheat field from eastern Washington in the Palouse region, taken back in 1970. Just for calibration, this is 35 years or so after the establishment of the USDA's Soil Conservation Service charged with preventing erosion in the United States. And you can still find places in the country where this process is still happening. But what happened here? You don't see any plants on the landscape, right? This is after plowing, after tillage. A rainstorm hit before the next crop came in. That rainstorm encountered a bare and very erodible land surface, and those little channels were carved into it. We would call them rills in my profession of geomorphology, and that basically means small channel. You can wipe it out with a single pass of the plow, you can kind of erase it. How important are these over time? Well, this next slide basically is the one I like to use to illustrate the magnitude, how all those little channels can add up to big effects over time. This is another winter wheat field in the Palouse, so it's taken by Vern Kaiser back in 1961. And that fence in the upper right-hand corner is the fence around a farmer's water cistern that was in place to basically prevent him from plowing over his own water supply. And so it's basically to protect the stuff off to the right. But off to the left, it was planted in winter wheat, sort of a wheat fallow rotation for the 50 years from 1911 to 1961. Nothing else happened in that field. Just those little kind of rills could happen anytime it rained after a plowing, and the soil would be washed off. This cliff developed at the edge of the field. Now, how big a deal is this? It's hard to tell on this negative, but see that black thing there? It sticks up a little above my finger, that little black line? That's a 1 foot increment on a survey rod, a stadia rod. This is a 5 foot cliff. 5 feet of soil erosion in 50 years. That's about a foot a decade, about an inch a year. There's nowhere on earth that soils form that fast. Now you should be sitting there thinking, well, yeah, Dave, isn't that a pretty extreme example? Well, yeah, of course it is. That's why I use it. It's meant to basically make you ask that question. It made me ask that question. Of course, I loved it when I found the historical picture, and the nice thing about historical photographs is you can use them. But how typical is that kind of magnitude of erosion? Let me show you another example from American history, the American Southeast. This time over a much broader region than around a single farm. This is the Piedmont country. This gray noodle is the Piedmont country, the hill country from down here from Alabama all the way up to Virginia up there in the other corner. And what the coloring shows you is the magnitude of post-colonial soil loss off this landscape that was worked out by geomorphologists. And you'll notice that there's an awful lot of 4 to 10 inch, this gray stuff, this gray color, 4 to 10 inches of soil loss. The black stuff is more than 10 inches of soil loss. This region was one of the original breadbaskets of the American colonies. It was a major agricultural region in the 17th and 18th centuries. How big a deal is 4 to 10, more than 10 inches of soil loss off this landscape? If you go back and reread the journals of the farmers who first settled this area, or the Western farmers, the European farmers who first settled this area and started plowing the soils up to plant tobacco and other crops, you'll find that they describe 6 to 12 inches of fertile black earth above the subsoil. This map shows you that we eroded almost all of it off over the course of just a couple hundred years of post-colonial agriculture. How did that happen? Think those rills. It probably wasn't as extreme each year out here back east, but think what a good southeast rainstorm could do on a freshly plowed field, and then think what that could do maintained over 4 or 5 generations of farmers. It starts to put into perspective the idea that we could quite literally, that farming societies could quite literally plow themselves out of business over the course of a few centuries into perspective as maybe not such a crazy idea after all. So think what the Romans could have done with an 800-year run at central Italy. Has anyone ever been to the ancient port of Rome, Ostia? It's nowhere near the coast. It's miles inland. Why? Because the soils of central Italy washed down, built out the coastline into the Mediterranean, abandoning the docks from the ancient port of Rome. You can find similar examples all around the Mediterranean. Think what the Greeks could have done with a 1,000-year run at southern Greece. It starts to put into perspective the idea that soil erosion could really impact human societies over the long run. You can also go out today and find examples where you can still read that signature in the landscape. I got approached a few years ago from a TV show that was trying to do a 3-part series on the geological history of North America. And I got approached sort of late in the game to try and do something because they realized that they were down to having about 5 minutes of time left in the series, and they had not done anything about the soil. They'd kind of just left it off the agenda. So I was asked, what could you do in like 3 minutes or so that could illustrate the history of soil, particularly the recent history of soil in North America? I said, well, let's go to a tobacco plantation in North Carolina, and let's get a white tablecloth, and let's go dig a hole in that conventional tobacco field, and let's look at the soil. That's the soil over here. It looks a lot like beach sand. In fact, it is beach sand. It's ancient beach sand, but there's not much organic matter in it. There were no worms in it that I could find. This was in the middle of the tobacco field. We then went next door to the forest that had been allowed to regrow for 100 years. Right next door, same soil, same climate, same everything, different land management. Check out the difference in the color in the soil. That's mostly due to organic matter. What's another name for organic matter? Carbon. If we look at the state of the world's soils globally, we've actually reduced about 50% of the organic matter content. The carbon that's in soils that was in soils is no longer in our topsoil. It's actually a lot of carbon that's gone into the atmosphere from plowing and degrading soils globally. And this gives you a bit of a sense for what we did in terms of turning the original forest soil of the southeast into the stuff over there on the right. And if you were a farmer, which would you rather be trying to farm? Well, I think almost every farmer I've ever met is going to pick the one on the left. So in researching dirt, I did something that I really wanted to convince myself of before I published the book. And that is, when you look back through history and you're looking at archaeological papers, archaeological data, you're reading sort of the books of Roman agriculture, you're triangulating arguments, but there's no direct data on how much soil was lost off a field. We have a lot of data in the modern world. I wanted to basically go and research the modern literature on rates of erosion to see, do the numbers pencil out in the way that I was thinking that they did based on this putting together the historical part. So I basically went to the library for 3 weeks and gathered up all the information that I could on rates of how fast are the world's farms eroding? Who's got data? How fast do the world's landscapes naturally erode? How fast is the pace of geological erosion? And how fast are soils built? How fast does nature make soils? And I'm going to boil down all that data into a single table for you. I put out a paper in the Proceedings of the National Academy of Sciences at the same time the book came out that has all the data in it. And if you're really interested in this subject or want to do a term paper on it or something, steal my spreadsheet. It's online. All the data behind this is there. No one ever has to compile this again. So what I do, I basically, in those 3 weeks, I found something like 1,400 different studies. And the types of studies are over there on the left. The average or the median, so it's the kind of average for half the numbers are lower, half the numbers are higher. So it's the one right in the middle on the right. And those numbers in parentheses basically show you how many peer-reviewed academic studies I compiled to present the average that's shown on the screen. And the bad news on this plot is that red number up there. Because modern conventional agriculture, and by conventional I mean pretty much plow-based, tillage-based in this case. We'll get into some other stuff a little later. But conventional tillage-based agriculture, global average soil erosion rate is about 1.5 millimeters a year. Sounds like another small number, right? Your fingernails grow 10 times faster than that. This is something that only a geologist might appreciate, perhaps. But 1.5 millimeters a year as an erosion rate is screamingly fast when you think about having geological time to play with. And there's blue numbers at the bottom, the erosion rate at our native vegetation, erosion rates, soil production rates, rates at which soils are rebuilt or produced, and long-term erosion rates, geological erosion rates. Those are all in the order of 1% or 2% of a millimeter a year as a global average. Pretty slow. Couple orders of magnitude slower than modern agricultural fields are eroding, though. The good news lies in that no-till number, that second line, because that's from farms. That's from areas that are actively farmed, but that use no-till techniques. Techniques of farming that do not rely on the plow, that don't invert the soil, that plant through the crop stubble from last year. There's various ways to do no-till, but agricultural methods that don't disturb the soil to the same degree as tillage. And you'll notice that that's colored blue because it's a lot more like those other blue numbers than it is like the red number. That's the good news. The bad news is that viewed globally, that kind of farming is still considered alternative agriculture. So anyway, I want to invite you to basically think about this problem because I've just given you all the data that you need to do a rough calculation on what the lifespan of an agricultural civilization ought to be under a net soil loss that we kind of have with contemporary tillage. Why is that pertinent? Well, it's kind of a check on what I saw in the archaeological world. So this is the kind of way a geomorphologist would think about it, who happen to have a napkin to do this kind of calculation on. But if you take that net soil loss of about 1 millimeter a year, and I'm trying to be conservative because I could have argued for more like 1.5 millimeters, take 1 millimeter a year, erosion of that typical 0.5 meter to meter thick hill slope soil would just take 500 to 1,000 years. That's about the average lifespan of agricultural civilizations you find in the historical record, with really big exceptions that are really important. And those exceptions, of course, are the major civilizations that developed along big floodplain rivers like the Tigris and the Euphrates in Mesopotamia, like the Nile in Egypt, like the Indus and the Brahmaputra in India, and like the big rivers that flow off the Tibetan Plateau across China. Those are societies that have been able to maintain tillage-based agriculture for thousands of years. And how'd they do it? Well, they're on floodplains that get replenished. The minerals get replenished every year. They're depositional environments. Where do you go in the world to find some really good ancient examples of societies that degraded their land and have not prospered? Go to the headwaters of each and every one of those systems. Go to Syria. Go to Somalia and Ethiopia. Go to the Tibetan Plateau and the seat of the original seat of Chinese agriculture. Go to the Himalaya in India. These are societies the loss of their soil essentially was subsidizing the prosperity of civilizations downstream. So now that I've gone through the sort of historical examples and looking at the Dirt book, and perhaps depressed anyone who hasn't read it already, this is where I started to ask myself the question of, well, what would it take to turn around this historical pattern of soil degradation and soil loss? And could we actually reverse it? Are there farming methods and practices that could run this in reverse? And that's a question I wrestled with for a fair while. I took some time off to actually write a book about the relationship, a non-controversial book about the relationship between science and religion in between dealing things with soil. But I eventually got back to it. And what led me to it was essentially insights that my wife started to teach me in the yard. She's a biologist. I'm a geologist. What does it take to actually make healthy, fertile soil? It's the marriage of geology and biology. So it's not all that surprising that two people like us would sort of think about these kind of things. But the catalyst that ended up to us writing this book together on the microbial world was actually something that I never expected to lead to a book, let alone actually any insight. And that catalyst was buying a house in North Seattle. I got tenure at the University of Washington a few years back, and when we did, we were like, okay, we're going to take that plunge, and This is the place that we bought, and I'm showing it to you because one of the things that Anne really wanted to do was make a garden. And this house had a house and then a side yard that was what I like to call an old growth Seattle lawn. It was 6 inches of tangled roots. It was deemed unacceptable by the chief gardener, and we decided that we would peel it off and try and basically plant something more interesting. And what we found when we did that and peeled the lawn off, as you can see here, is that we found that we had that really wonderful, rich black earth that North Seattle is known for. Yeah, no, we had glacial till. We had really crap soil. It was basically nature's concrete. Bits of Canada that got scraped off by the Puget Lobe as it advanced south, got bulldozed down into Seattle, melted out and spread around by meltwater streams, then overrun by a mile-high wall of ice 3 times the height of the Space Needle. And then it all backed off and left us with nature's concrete. This was not what we were hoping to find. And you may be sitting there going, well, why didn't the geologist and the biologist dig a soil pit in the yard of the house they were thinking of buying and find out what kind of soil they had? And we have absolutely no defense. We thought about, notice the neighbor's place back there. That should reappear in a few slides. But basically, we realized that we had dirt. We didn't have soil. We had the geological half of soil. We were missing the biology. We didn't have the organic matter. We didn't have the living organisms. And that's something that Anne took it on herself to try and remedy in what we in the book called her organic matter crusade, because she started collecting as much organic matter as she could from the neighbors. She'd rake up their oak leaves and bring them back, and you'd be surprised how friendly the neighbors in a city get when you just show up with your racing stripe painted wheelbarrow to take, rake up and take their leaves away for them. But they didn't realize what they were losing. They were losing they were giving away fertilizer, basically. So we also got coffee grounds from the coffee shops down at the street, excellent source of nitrogen. We entered the Zoo-Doo lottery where the Seattle Zoo gives away the composted herbivore turds. And we kept entering it and we kept winning. And we were thinking, and we started to feel really special until we started to suspect that maybe everybody wins all the time. But we started bringing as much organic matter as we could back to the yard because that's the part that was missing. And how fast did that actually work to help to rebuild soil in our yard? Well, this gives you a picture of the soil pit that we dug about 3 or 4 years into this intensive composting and mulching. We also got wood chips from arborists that we'd put on the soil. We started composting our kitchen scraps and got a worm bin. We did everything we could to put organic matter back in the yard. This is about 3 to 5 years later. Those are Anne's pruning shears for scale. You notice that down at depth in this pit, we still have the glacial till. We didn't dig anything. We were too lazy to actually dig stuff. We just kept composting and mulching, putting stuff on the top, and when it would disappear and break down, we'd put more back on. And you can see that up there at the top, a good layer of mulch. Notice that the plant roots are going down to the till and going sideways. They're not really growing into the till. But also notice that we've got about 2 inches of halfway decent soil there after only about 3 or 4 years of this soil building activity. Now think back to those numbers I was showing you in terms of the rates of natural soil production, 0.02 millimeters per year. Here we've got 2 inches in 5 years. That's like 4 inches in a decade. That's like a meter in a century. And remember, I'm somebody who thinks a century is a pretty short unit of time. What's the average soil depth on the planet, on hillsides? 1/2 meter to 2/3 of a meter if you consult the UN Global Soil Database. Here we're on pace to essentially rebuild a really thick, fertile soil in under a century. This is beating nature at her own game in terms of pace of soil production. And there's reasons for that we could go into afterwards. But basically, Anne and I started to realize that we were restoring our soil at a pace in our yard that was actually in a policy-relevant time frame. Years, not centuries. This shows you basically what we've done, where this is the soil that we started with in our yard. It had about less than 0.5% organic matter. The soil we have now is this stuff over here. It's got between 8 and 10% organic matter. That translates into us having stashed something like 8 tons of carbon in our yard. That's a lot of carbon to put in the ground. Drop in the bucket in terms of the global carbon budget, obviously. But we did this at home gardening. It also led to an explosion of life above ground, which really improved our lives. We spend our lives, in the summer outside now instead of inside. And I used to think that that lawn was great because I could get my grad students over to play croquet once a year, and the dog would chase a tennis ball across it. But it wasn't a garden. We now have this lush, rich, beautiful garden that enriches our lives. And also notice the neighbor's house back there. We can't even see them anymore, which is really nice. If there's, they're perfectly fine people, but I did not want to watch their kids grow up. But we also, this exercise of going through and realizing the connection between the changes below ground in terms of restoring our soil and the explosion of life above ground opened our eyes to looking at the importance of the microbial world in terms of supporting the above ground world that we know of. I mean, Anne's the kind of biologist that was trained to study salmon and tortoises, the kind of things we can see with our senses. And I trained to study the dead stuff underneath. But we realized in looking into sort of why it was that adding all this organic matter could lead to such rapid improvements in the soil and such a rapid explosion of life above ground, it led us squarely down into the world of the rhizosphere, which is essentially the zone around the roots of plants. And it turns out that if you want to find a zone on this planet that's full of life, microbial life in particular, that's the place to look. It's one of the most life-dense zones on the planet. And it turns out that all those life forms are living around the roots of plants, not to attack the plant roots, but because the plants are feeding them. Because something that Ann and I were not taught in the soil science classes that we took in graduate school was that not only do plants take up water and nutrients and minerals from the soil, and that's what we were sort of trained to think of roots as, or straws to draw nutrients out of the ground, but roots are actually a two-way street. There's been enough studies done now to look at what plants are pushing out of their roots into the soil to be able to say with confidence that an awful lot of different plants will push out 30 to 40% of the material that they will photosynthesize through combining carbon dioxide and water to build sugars and other complex organic molecules. They'll push 30% or more of that stuff out of their roots and into the soil. Not all plants do this, but many do. And they're not just pushing out sugars. They're pushing out sugars, proteins. There was even a paper that came out last spring documenting that plants are pushing lipids, fats, out of their roots and into the soil. Now, what does that sound like? Proteins, carbohydrates, and fats. Sounds like food, doesn't it? Plants are pushing food into the soil. That's why there's so many microbes living in the rhizosphere. Now, if that was to feed pests and pathogens, doesn't that sound like an absolutely wretched evolutionary strategy? Yet when you go back in geologic time and you look at the very first the fossils of land plants we have from some 450 million years ago, they have mycorrhizal fungi intertwined with their roots. These partnerships between microbes in the soil, bacteria and fungi, and plants go back to the first land plants on land. So the plants aren't doing it just for fun or to be nice. They're feeding that life, they're feeding those microbes because they get something back in return that's of benefit to them. So how does that work? Essentially, if you blow up the root zone, the zone around the tip of a root in a plant, you're basically getting a window onto a biological bazaar where all kinds of trading is going on in terms of nutrients flowing out of plants and nice things that help the plant flowing in. And so these black arrows here show that the plant exudates. The things the plant roots are exuding are going out of the root into the soil, and they don't make it very far. They make it about 1 millimeter to 1 centimeter out into the soil before they get eaten. Why? Well, because there's so much life there at that subterranean buffet. And what does anything do with a good meal after you've eaten it? Well, you metabolize it, you process it, and your body eliminates the part you didn't use or the parts that you transformed that food into. And we're accustomed to thinking of that as waste. In the microbial world, let's call it metabolites, just to be polite. Those microbial metabolites then are produced in the zone right around the roots where they can be easily taken back up by the plant. When we learned that some of those microbial metabolites include plant growth promoting hormones, we were kind of floored. Who would have thought that one form of life, bacteria, one kingdom of life in the soil would be producing growth hormones for some completely different sphere of the natural world? The microbes were making things to make the plants grow bigger And they also promote, manufacture chemicals that help with tee up plant defense, tee up plant communication. Mycorrhizal fungi in the soil that partner with plant roots are going out and actually mining mineral micronutrients and things like phosphorus out of soil particles, bring it back, and in effect, trading it to the plant for sugars and proteins. These are examples of symbioses, of partnerships between organisms. The plants are helping to feed the microbes, and the microbes are helping the plants to be not only to grow and acquire their nutrition, but to be healthy and defend themselves. These are real symbioses that turn out to be a key for how the botanical world both grows and protects itself. And this allows us to think a little about what happens under different ways that you feed the soil or feed plants. And I hadn't really thought about a plant having a diet before. You know, I knew that they grew in the soil and that they needed things from the soil, but it also helps explain part of what some of our problems with 20th century agriculture were. So if you basically take a plant that is growing in a soil where you've degraded the organic matter, so you need lots of chemical fertilizers to grow a lot of plants, and we all know that if you add a lot of nitrogen to a degraded soil, you can get a boost in productivity out of it. The secret that we don't often share is that if you have a really rich, healthy, fertile soil to begin with, you don't get any benefit from adding nitrogen to it. There's no benefit. What you do is you waste your money on fertilizer. And so basically, if you have a plant that's grown in a nutrient-poor soil, but you give it all the macronutrients, all the N, P, and K that it needs, it won't invest in its root system. It's a fairly well-known agronomic phenomena. And it will also not, therefore, be putting out as many exudates into the soil. So it's not recruiting the same cadre of beneficial microbes in the soil, which means that it's getting less of the good microbial metabolites and less of the mineral micronutrients that soil life was providing to the plant in the first place through those symbioses we just talked about. This helps explain the observation that the global demand for pesticide went through the roof after the global adoption of fertilizers went through the roof. Why? Because we basically disarmed our plants' defensive systems and changed the communities of life in the soil through intensive tillage and intensive fertilization. If you look at essentially what Ann and I call the soil health diet, or the way plants grow in very organic matter-rich soils with a lot of life in it, they will invest in extensive root systems, put out a lot of exudates. They're getting a lot of beneficial microbial metabolites, plenty of those mineral micronutrients, and they can grow just fine because they'll get the macronutrients they need as well. And if you think about what this means, the middle thing in terms of mineral micronutrients, what that means for the quality of the food that we eat, maybe here we also have a partial explanation for the observation that the micronutrient content of our food has gone down dramatically in the last half century. Of course, there's other things like crop varieties and diluting the effect from just growing a lot more as well. They factor into that as well. But the point here is that we can start thinking about plants as having a diet, and it helps us rethink basic agricultural assumptions. What we can also show, and we talk about in the hidden half of nature, is that these relationships between the microbial world and the rhizosphere and the plant roots, they are mirrored inside out in the human gut. Those systems are virtually the same thing inside out in terms of nutrient acquisition, in terms of chemical signaling, in terms of teeing up the defensive system, our immune system, or the plant's defensive system. This is the way nature works. And it's a fairly recent revelation in terms of how widespread and important those kinds of microbial ecological relationships and symbioses are to the organisms that serve as their hosts: plants, people, other animals. And I won't go too far down the medical side of things. We do that in the hidden half. I want to focus tonight instead on what this means for agriculture. And basically, when I realized how fast, when Ann and I realized how fast we'd restored life to our soil and the implications of it, and dug into it enough to understand the microbial connections, we started asking ourselves questions like, well, could we do this on farms? You know, does this scalable? Could you take the kind of techniques that we use in our yard, would they apply to farms around the world? And not being a farmer, I didn't want to basically sort of like be telling people how to do this. I figured the logical way to work it out is to go to farms where farmers had actually already restored health and fertility to their land, bring a shovel along, ask them how they did it, then dig holes and look at their soil for myself, look at their neighbor's soil, sneaking over the fence line to see what that looked like. And I took 6 months off to basically go around the world and talk to farmers who had done it. And you'll notice the color difference in these two soil cores. They're from Ratan Lau's long-term no-till experiments at the Ohio State University, where he's able to turn this kind of a soil into this kind of a soil over a little more than a decade. How? Compost and organic matter, mulch, compost and mulch. Essentially the same kind of basic ideas that we're using in our yard. So I visited farms around the world to places that people had rebuilt their soil health and looked at how adopting the principles of conservation agriculture had allowed them to rebuild the fertility of their soil such that they could achieve conventional crop yields with far less oil and far less chemical inputs. So you may be sitting there going, okay, well, what is this conservation agriculture thing? It turns out that these three principles of conservation agriculture turned out to be the common elements among all the farmers that I visited who'd had remarkable success at rebuilding their soil organic matter, rebuilding their soil life, rebuilding soil health, and essentially restoring profitability to their farms. First principle is don't disturb the soil. Don't dig, don't plow, don't disturb the soil life. Second principle, maintain a permanent ground cover. Always have green plants covering the surface and always have roots penetrating the surface. Those two things together help really shut down soil erosion. And if you're going to build soil health and fertility, that's the first thing you have to do is shut down soil erosion. Because if you don't, where is the most fertile in the soil? The top soil. Where does the soil erode from? The top. So if you have soil erosion going on, you're basically rowing against a big current because you'll be losing it faster than you're making it. So those two principles, basically no-till plus cover crops. Third principle, diverse rotations. Grow more than one or two crops. Those three things were essentially the recipe that all these farmers that I visited, that I'll show you a few examples of in a minute, had in common. What they didn't have in common was their specific practices. I'll show you some examples from Africa, some from North America, and as you can imagine with different kinds of soils around the world and climates around the world and technologies around the world, the way you would implement these principles can be very different on the ground. The same practices that might work in, say, Western Washington might not work in Eastern Washington. You need to tailor things for the landscape as well as for the farmers, the crops they're growing, and even the topography on individual farms. But what I found is that the principles at the higher level really translated across. And you had a question, if it's still...
I was wondering what size of farms you studied?
Oh, I will show you that, but basically everything from small subsistence farms in Ghana that were about less than half the size of this room to 20,000 acre farms in the Dakotas. These principles scale. The practices you would use to scale them don't. On Ghana, they were using machetes and hand planting. In the Dakotas, they were using GPS-driven space-age prairie crawlers. But the principles they followed were similar. The way they implemented them were adapted to local conditions. And that's really, really important. That's one of the take-home messages of both the book and what I want to say tonight, is that there are general principles that we can apply to build soil health that are very different than the general principles that underpin modern conventional agriculture. But there's a lot of learning and research to be done to figure out how to tailor these new principles to different landscapes. So in case you're wondering, well, how do you do no-till planting? If you've never seen a no-till planter before, this is one. This is Ohio farmer David Brandt, who will return in a few minutes when I'll talk about him a little more. He's modeling his no-till planter. I just want to basically show it to you for the simple idea that it's a technological device that is an alternative to the plow. And what it does is it basically cuts a trench in the soil. It's dragged this way. You put it behind your tractor, drag it off that way. It cuts a trench in the soil. That white thing drops a seed down into the trench, and these wheels close the vegetation that's still on the surface back up over it, so that a freshly planted field looks like this. This thing has been running that way. You can kind of maybe see some of the trenches behind there. They're hard to see. Compare that in your mind's eye in terms of disturbance to what I was showing you from the Palouse. It's like night and day. This is like almost a completely undisturbed field, but it's freshly planted. What about managing cover crops? There's different ways to essentially manage cover crops. A lot of no-till farmers these days use the herbicide glyphosate to essentially manage their cover crops or to basically deal with weed pressure. Cover crops are a different way to do that. This is Jeff Moyers from the Organic Rodale Institute in Pennsylvania. He's modeling what is known as a roller crimper. It's basically a steamroller-like drum that has big metal chevrons on it that you put in front of your tractor. And if you couple that with the no-till planter behind, you can take a field that has cover crops in it, mow it down with your roller crimper to basically turn that stuff into mulch, and then plant directly through that mulch with a single pass of the tractor. Because you got the roller crimper on the front, no-till planter on the back. That saves you diesel because you're not driving, because the next time you go to drive across the field, you harvest. So you can save a lot on diesel up front, and you can save a lot on other things, as we'll talk about as we go. But these kind of devices won't always work in all places. If you had a really wet soil or a wet clay soil, that roller crimper might not actually crimp the crop, or depending on what you're growing. The point again being that there's different ways to do it. Another way to manage weeds is with livestock. I'll tell you a little bit more about that later. But let me show you 4 farmers and sort of some of the differences that they had. This is Dwayne Beck. He's a farmer and researcher at South Dakota State University, where he manages Dakota Lakes Research Farm. It's in the area that is featured on the cover of the Dirt book. So you know that agricultural equipment being buried by dust from the Dust Bowl, that's in his neighborhood. That photo, and one of the reasons I went to visit him is he's in that neighborhood. But he's been pioneering the development and application of no-till practices in that region for the last several decades. And he took me on a 300-mile drive around Dakota Lakes Research Farm. I saw 3 plowed fields. Most of the people in his neighborhood have adopted not only no-till, but they've now moved to cover crops, and they're experimenting with diversified rotations. And this just shows you essentially there's no bare ground on his research farm. There's cover crops coming in between the remnants of the last crop. But what he's done is that by adopting no-till, cover crops, and complex rotations, those 3 principles of conservation agriculture, he's managed to greatly reduce their use of diesel, fertilizer, and pesticide. And by greatly, I mean by more than half in each case. Up to 80 or 90% in terms of the pesticide and the fertilizer in some of the fields. That translates into a direct savings to the farmers. But what did it do to their yields? You know, the first thing you often hear when people talk about, well, we need modern agrochemical intensive agriculture to feed the world or we'll all starve, is that, you know, if you start using less of them, we're going to lose yield. Look what happened to their yields. They went up. Soybean yields went up. Corn yields went up. So it's not a question of the economy or feeding the world versus the environment. It's kind of a win-win, actually. The farmers save money by spending less on inputs, but they grow just as much or even maybe a little more. And the example is not unique.
I'm wondering why you think the paradigm exists, that it would cost more, or that it would cost profit and cost yield to move to a complex rotation.
Well, it's moving to the combination of all 3, and basically what they did is they've almost eliminated their agrochemical use. They're almost organic. So they've become essentially what I teased them as being organic-ish, where they're using very few inputs. And if you look at most of the comparisons that have looked at organic versus conventional yields, people will argue there's a yield penalty for going organic. Part of that is the way things are averaged. Part of it are the nature of the studies that are lumped into meta-studies. What I was so interested in here is that basically the standard thinking in conventional agriculture is you need more inputs to have a bigger yield. That's why they use more of them. This is completely counter to that. And it's based on a change in thinking about the soil and a change in practices. And it's kind of a revolutionary way to think about changing farm profitability. Instead of trying to grow more food, you grow the same amount of food but spend less to grow it. It's a different way of changing the bottom line. Farmers all over this country are very concerned about yields and maximizing their yield. But sometimes the way to a maximum profit might not be to maximize yield. But the thing that I found so encouraging about these results is that yields both either stayed similar or went up, and the input use went way down, which means really that it's just much more efficient. Yeah?
That looks like a mulch systems, so is water conservation a part of this as well?
Yes, water conservation was a big motivation in the Dakotas. For every percent of organic matter you can increase in the soil, you can hold a lot more water in the soil, the equivalent of a few inches of water in it. What they were basically finding when they went to no-till is that water didn't run off their fields anymore. It actually started to infiltrate into the soil where they could keep it. And if you have a vegetative cover, a mulch on it, you're basically going to keep it in the soil where you want it. So water conservation for these guys was actually a really, really big factor. Yeah?
You mentioned their complex rotation. Is it soybeans 1 year, corn the next, and then what happens after that?
They have a lot of different, they have lots of, it's a research farm. This particular farm has lots of different combinations. Corn, soybeans, wheat, rye, barley. They're growing different kinds of things, but they also are getting cover crops into the rotation as they go.
Do they lose a crop where they have the cover crop, or are the cover crops the same year as you also get another crop?
They're not using the cover crops as a substitute. They're basically using them in between.
Okay, that's good, because a lot of times the argument is, well, you've lost that time that you had a cover or some other.
No, what's actually, and these yield numbers are actually deceptive, because what the transformation in this region allowed them to do is they used to have a wheat fallow rotation. So they would only farm half their farm each year. Once they make this conversion, they farm the entire farm every year. So in reality, their yields have doubled, not on a per hectare basis, but on a per farm basis. But that's a whole, that's been a major effect on the local economy, because they're basically able to use their whole acreage every year.
Question over here, Dave.
Yeah.
Are there any long-term studies for complex rotation that are being implemented?
There have been studies on the effects of crop rotations on yields going back to the 1930s. What there are very few of are studies that are long-term that look at all three elements of no-till, cover crops, and complex rotations. So studies that look at the full system of conservation agriculture are few and far between. So one of the things I had to do in Growing a Revolution was read all the meta-studies that had looked at the comparisons of things where they would just go, oh, well, does no-till increase soil organic matter? Well, if you just do no-till, you get answers that are actually all over the map, because some no-till things would have cover crops, some wouldn't. Some would actually take the crop stubble and send it off to the biofuel plant. Others would keep all the organic matter and husband it, and that's where the real difference lay. Same thing with, and that's very similar to the organic versus conventional yield comparison. It's kind of, those are thick, those are not terribly informative labels anymore when just viewed on themselves. But so what we're really missing are a lot of long-term studies of this full system of conservation agriculture, which is one of the reasons I went to farmers who'd been doing it. Some of these guys have been doing it for a decade or two, and you could actually see the long-term results. Yeah.
Could we go back to what I think this original question was, and I'm sorry I don't know your name and I'm not sure I heard you right, but I think your question was why and how did mindset get put in place that even now, I would wager, the majority of farmers in the Midwest, if you suggested these three principles work, would probably laugh. So the question I think I heard was, how did that mindset get put into place?
One of the reasons, as far as I can tell, that the rise of fertilizer intensive and then following on that pesticide intensive agriculture was so successful in the mid-20th century is that we had degraded our soils so much that you saw a big boost in yield from using those inputs. If you have, we had already gone a long way down the road of soil degradation at that point.
So the Green Revolution, for example, was a miracle because of the horrific conditions that were already in place.
The Green Revolution, the adopting fertilizer receptive varieties of crops was an extra boost, but it was all that much more impressive based on what we had done, or the state of soil at the time.
Does that help? Is that kind of what you were getting at?
Yeah. What I also heard him mention though was the kind of like the business mindset to farming, right? Where you need increased input for increased yields, when in reality that's not necessarily the case. So yeah.
Right, but farmers are advised that that's the case. I mean, if you look at who is advising farmers in the United States at present, an awful lot of the people who are advising them are trying to sell them something. When I left Dakota Lakes Research Farm, I basically asked Dwayne, would the kind of principles and practices that you're using here work on small subsistence farms in Africa? And he said, don't talk to me about that. I don't know, but I know someone who's already done it, so go talk to him. And that gentleman was Kofi Boa, this gentleman here. And I like to point out his hat, got dirt, get soil. That's the first thing I saw when I got out of the car and met him. And I was like, I like this guy. He's got the right idea. He takes these same principles of conservation agriculture and applies them in a very different kind of setting and context. He's in equatorial West Africa, Ghana, and the farmers he works with, notice that the land is mulched, there's no bare soil, but they also have 3, 4, sometimes up to 6 or 8 crops in one field at one time. These are small farms, they're mostly hand-worked, mostly subsistence farms, and they're bringing diversity in at the same time. So you can think diversity and crop rotation sort of sequentially, or you can think of it sort of mixed in the field. The key things are keeping the ground covered, not disturbing the soil, and having a diversity of plants. And what has his pioneering efforts to figure out how to apply these principles in his environment, how they played out, he's basically taking the people around his village from their traditional slash and burn style of agriculture, which they had gotten to the point where they were essentially burning the same fields each year. And slash and burn works really well if you can leave the land alone for 10, 20, 30 years in between times of intensive agriculture for a couple of years and let the land recover. If you have to plant every year, that burning basically helps draw down soil organic matter, and they had greatly depleted the organic matter of their soils. Got them down below 2% in an environment where they had originally had 4 to 5%, which is actually pretty high for tropical soil. So what did Kofi do by taking them to no-till with cover crops and having a diversity of crops in the field at one time? They basically shut off erosion. It went from about 1,700 kilograms per hectare a year down to less than 80 with their methods. They basically turned off soil erosion that had been a big problem. And look at what happened to their yields. Their corn yield tripled, their cowpea yield doubled. This is without extra inputs, no fertilizer, no GMO seeds, no pesticides, although they do use a little herbicide on occasion when they need it. But those kind of boosts in yields are comparable to what you could get with Green Revolution technologies. But this is with no inputs. And there's a pretty simple reason in my mind why the Green Revolution technologies wouldn't feed farmers like inhabit the region around Kofi's village. They don't have money to buy fertilizer, they don't have money to buy patented seeds. They needed a different way to think about it. And this different system of farming practices gave them a real benefit that could actually fit into their style of farming. And it was all about figuring out how to adapt the principles of conservation agriculture to their landscape. David Brandt is another farmer that I like to highlight. He is in Carroll, Ohio, and he's somebody who's been practicing no-till farming for 44 years, ever since he came back from a stint in the Marine Corps in Vietnam. And he basically considers himself a rancher. But his livestock are shown on this side. He's a microbe rancher. He's a corn and soy, commodity corn and soy farmer. That's what he sells. But that's not all that he grows. In between his corn and soy crops, he grows cover crops with up to 10 or 12 different species in the field. He's holding a daikon radish there. But as much as he could get, if he could get those to this farmer's market in Seattle, he doesn't grow them for sale. He grows them to feed his microbes. He crimps them at the end or kills them at the end of the season and basically lets them rot in the field. And he's using those deep-rooted species to go down and get nutrition from the subsoil, bring it up into their bodies. When they die, it rots and gets incorporated into the topsoil. That then can get taken up by his corn and soybeans. That's his fertilizer. And notice his neighbor's fields in the background, behind that car up there. They look kind of yellow, don't they? Those are soybeans. They're kind of sickly. Notice there's little patches of green in that sea of yellow in his neighbor's field. Those are glyphosate-resistant weeds. They've been sprayed 3 times the season I took this picture. Can't kill them. Up to a quarter to a third by visual estimation of his neighbor's fields are covered with glyphosate-resistant weeds. That's a direct hit on their yields. David Brandt doesn't have any weeds. He plants them, and he calls them cover crops. He kills them before they go to seed. He uses them as green manure. So one of the things that helped turn me into an optimist on this issue was working through with these farmers the economics of their farm. Because as a geologist, I'm probably the last person you ever want to ask for investment advice or financial advice of any sort. But I wanted to know how these practices had played out for them as farmers. And this basically walks you through the summary for David Brandt's farm in comparison with the county average, what his neighbors are doing. And his neighbors are full tillage. They use about 200 pounds of nitrogen an acre and 2.5 quarts of Roundup to grow their harvest. And I just want to emphasize, Brandt is not an organic farmer. He's a conventional farmer. But his neighbors are using a whole lot of inputs. That costs them about $500 an acre at the corn yield of 100 bushels an acre that they were pulling off of those fields, given the weed problem. At $4 per bushel, they were losing $100 an acre. That's a great business model, isn't it? The more you work, the more you lose. At the time, this same year, I found a study in Iowa that 25% of the farmers in Iowa lost money on every acre they planted. Iowa has some of the best soil in the world. That's kind of an astounding indictment of conventional agriculture, that hardworking people on some of the best soil in the world could lose more money the harder they worked. Something's wrong with that. You look at what David Brandt was doing with his 44 years of no-till with cover crops, where he'd managed to restore fertility to his land. He'd taken, when he got his farm, it had less than 2% organic matter. It's down about 1% or 0.5%. He's built it back up to 6 or 8%. That's better than in the native forest where he is. He's restored fertility and health to his land, and he's not tilling, so he's saving on diesel right away. He's only using 1/8 of the nitrogen and 1/5 of the Roundup per acre. He's not an organic farmer. He's organic-ish, because he's just not using much in the way of inputs, because he doesn't want to buy them if he doesn't have to. His economics, he's spending $320 an acre to grow 180 bushels an acre at $4 a bushel. He's making a profit of $400 an acre, while his neighbors are losing $100 an acre. The other question you should ask that I do not have a good answer for is, why aren't all his neighbors just jumping to adopt his practices? If you can crack that problem, you can change the world. Last farmer that I think I'll talk to you about is a guy named Gabe Brown. He's a rancher that has livestock that you might recognize as livestock. He's reintegrating cattle onto his land, and he's a gentleman who really taught me that livestock can be an agent of soil regeneration as opposed to simply one of soil destruction. I got an introduction to the effects of grazing on landscapes by studying the California coast ranges for part of my PhD, and there, excessive dairy grazing in the valley bottoms in the 1880s and 90s caused great gullies to form that you can still go walk around if you go up to the Marin Headlands north of San Francisco the next time you're down in the Bay Area. I thought cows equal erosion. Cows are bad. And there's a whole literature in geomorphology I can point you to that will back that assertion up. Going to Gabe's farm, I realized that the problem's not the cows. The problem is how we were managing the cows, how we were grazing them, what we were doing with them. He practices what's known as intensive rotational grazing, where he's got a lot of cows in a small area and moves them around often. The idea is to emulate the natural grazing pattern of the buffalo that helped build the great carbon-rich grasslands of the American Midwest in the first place. And he's had remarkable results. He proudly wears the regenerative agriculture label, the idea being he's a farmer who's trying to rebuild the fertility of his land. And one of the things that he does that I thought was very interesting is, instead of using a crop roller or glyphosate, one of the ways that he kills off the cover crops after his cash crops is he lets his cattle come in and graze them all off. So they're basically eating his cover crops off before they go to seed, and then he brings chickens in to basically get all the fly larvae out of the cattle poop. And it dawned on me that what he's doing is he's using his livestock to accelerate the breakdown of those cover crops and essentially use them as fermentation tanks to process all that organic matter and put it back on the land in a form that plants can take up more rapidly than waiting for it to degrade in the soil. He's using cattle as a tool of soil restoration. What's it done to his soil? This shows you Gabe's hands, and in one of his hands he's holding the soil from his neighbor's organic farm. It's been a tillage-based organic farm for the last 20 or 30 years or so. And in his other hand, he's holding soil from his market garden where he grows crops for his CSA operation, and then he lets the cattle graze off those cover crops. Well, guess which one is the organic soil? It's not the dark brown one. The dark stuff, he's not a conventional farmer. He's another one of these organic-ish farmers. But he has so rebuilt the health and fertility of his land that it's incredible. These labels of conventional organic, when you get into the realm of people like Gabe Brown and like David Brandt, the sort of the idea of organic and conventional starts to kind of go out the window, and you start trying to think of it, well, what if we thought instead about practices that build soil health, that build the health and fertility of the land, and thereby allow farmers to use very few agrochemicals? Therein lies the real opportunity to transform agriculture. Because if we could transform conventional farming practices into these organic-ish practices, you could really change things. And the recipe for that, as far as I can tell, in interviewing these folks and in looking at their land and their soil and their effects, is ditch the plow, cover up, and grow diversity. It's those three principles of conservation agriculture. And if you think about what that represents in terms of how we think about the soil, it's a radical change in philosophy. Because what's underpinned modern conventional agriculture has been intensive tillage, intensive chemical use, and growing one or two crops, functional monocultures. This goes down that list and inverts them, 180 degrees on each one. And I haven't mentioned the words conventional or organic in trying to do that. This system can work in both realms. And in fact, if you look at some of the long-term hazards of organic agriculture, go back to the start of the talk. We didn't have agrochemicals in the Roman Empire. Long-term use of the plow, even in an organic setting, can degrade the land. There's certain conditions where you can actually build soil even with the plow with organic practices, but the key thing here is if we start thinking instead about soil health, we start thinking about labels a little differently. And what are the benefits of adopting these practices? Well, we can get comparable, if not increased yields. Greatly reduced fossil fuel, fertilizer, and pesticide use. That translates into higher farmer profits because you're growing as much, spending less to grow as much. And it also translates into less on and off farm pollution in terms of nitrogen pollution, phosphate pollution, and in terms of less fossil fuel use, less carbon pollution. It also can increase soil carbon. It can sequester a surprising amount of carbon in the soil. All those changes that I've shown you of soils that went from khaki to dark brown, if not black, that's all carbon. And also, it can help with water retention, which can be of great value in drought-prone areas. That seems like a lot of wins. I just want to emphasize again, this is not a question of organic versus conventional or GMOs versus organic. It's really a question of how to apply understanding soil ecology to build soil health and sustain, if not increase, crop yields using far less inputs. There's a path forward to doing that I think could actually appeal to an awful lot of conventional farmers if they knew about it and if they had assistance in figuring out how to tailor and adapt these principles to their landscape and their crops and their markets. And therein lies the values of demonstration farms, because it's very hard to get somebody to take a risk with their own livelihood. If you see someone else try it in your neighborhood and go, oh, that worked, I can do that too. That's a real value of places like Dakota Lakes Research Farm and Kofi Boa's No-Till Center in Ghana, is that they can show that it can work. So this gets us to sort of near the end, where I basically want to argue that we may be on the verge of what I'd like to think could become the next agricultural revolution. And so if you indulge me, I'll tell you why I think this would be the fifth one. Now, academics will argue about how many agricultural revolutions there have been, and I don't have a particular dog in that fight. I just think that we've gone through 4, and I've defined them the way I like them, and I don't defend that. I'm just telling you how I did it. The first one was the idea of farming in the first place, cultivation and tillage. Yeah, that was a revolution in humanity's relationship to the land. It was a really different and new idea. And that's the Greek goddess Ceres, the goddess of cereals. The second revolution was thinking about soil husbandry, the idea of planting legumes with your crops, the ideas of rotating crops. These ideas came up in societies around the world and became traditional ideas because they helped maintain the fertility of the land. And so if you think about those 2 out of those 3 principles of conservation agriculture, cover crops and crop rotations, they're not new ideas. They're really old ideas. What's new is combining them with the idea of not tilling. And being able to do that at a large scale. And this is my favorite quote from Leonardo da Vinci. We know more about the movement of celestial bodies than about the soil underfoot. How many quotes about science from 500 years ago can you point to that are still as current today as when they were first offered? We're still learning about the world of soil life and its relationship to plants and its potential agronomic applications. Da Vinci's words still ring true. The third agricultural revolution I like to think of as mechanization and industrialization, the rise of intensive fertilizer use, the use of mechanical tillage implements, and this is something that radically transformed agriculture in the 19th and 20th centuries. In the late 20th century, the fourth agricultural revolution in terms of the green revolution and biotechnology that I just like to lump into one, even though that may not be fair. But basically, we know that the green revolution resulted in higher yields. I'm not going to talk much about GMOs, but I want to basically point out that increases in crop yields have plateaued. We're not getting the same bang as we used to. And I think that there's a case to be made that this idea of adopting and promoting farming practices that can rebuild soil health really could hold the potential for another agricultural revolution. This one maybe not so much in terms of increasing total output, but cementing our ability to maintain that output over time, to sustain that output. We need to figure out how to merge the ancient wisdom of crop rotations and cover crops with modern technologies that allow for minimum tillage into new systems of farming that rebuild soil health and fertility. And I've shown you examples from farmers around the world who've already done it. This is not a theory. This can be done. Whether it could be done in all environments with all kinds of settings, well, okay, so that might still be a bit theoretical. But it's a challenge that I think we could rise to. And that if we are able to actually convert what we now consider modern conventional farming to these new regenerative practices along the lines of the folks I was talking about and who had adopted conservation agricultural practices and who had even brought livestock back onto the land, if we could change conventional farming to that style of regenerative agriculture, it actually really would change the world and have a tremendous impact that would ripple through environmental effects, it would ripple through other realms of endeavor. What could it actually help us with? It would help us with the problem of, first of all, restoring farm profitability, which is a problem in a lot of rural regions around not only North America, but around the world. It would help us feed the world. We could sequester carbon in the ground, which would help with the climate problem, and it could help with environmental degradation. Something like 1/3 of the world's continental landmass is devoted to agriculture. The future of biodiversity is in great part going to be written by what we do on farms around the world. And this style of regenerative agriculture won't solve any of those problems, but it will help solve all of them. And so I came away much more optimistic than I started. When I finished that Dirt book, I actually wrote 3 different drafts of the last chapter. The first 2 were way too depressing, and I decided I didn't want to put my name on it, I'd try again. By the time I got finished with Growing a Revolution, I was genuinely optimistic. I think we can solve the problem of soil degradation. I've seen economically viable ways to do it. And some of the biggest obstacles are our own thinking, our own habits. The way we've done things is the way we're going to do things, right? No, you have to think outside the box to completely change the way you're doing it. And this philosophy of regenerative agriculture with those key principles is a 180-degree shift from the main philosophy that's underpinned conventional agriculture for the last 100 years. So the first thing we have to do is we have to change the way we think about soil. And as easy as that may sound, sometimes that's the hardest thing to do. So anyway, I will leave you there. If anyone is interested in picking up copies of any of the books, I've learned to carry them around. I have copies, just see me afterwards. And if you have questions, I suspect I still have a bit of voice left to answer them.
So let's give Dave a hand. Questions? Must be more.
Yeah.
So you mentioned that you're optimistic about this because we can do it.
Doesn't mean we will, though, right?
That is, will we do it? What is the timeline for implementation that we need to offset people that are resistant to it? What would you recommend in timing?
Yeah, well, the great fallback that I have as a geologist is that, if we can make this transition in 20, 30 years, I'll think it's really fast. From a policy end, that may be, a long time. In sort of my life as a geologist, I've noticed there tends to be about a 10 to 20 year lag between things that leave the sort of the lab and start to go out and be adopted professionally. My suspicion is there's at least that same kind of time lag in this kind of a transition. I've seen, when I wrote that dirt book, hardly anybody was talking about soil and our ability to sustain it or to restore it. 10 years later, there are conferences every week of the year in farming communities around the country focused on soil health and rebuilding it. There's a groundswell of interest in farming communities from what I can tell. Either that or they just all found my number somehow. And I'm really impressed with the enthusiasm and the passion that a lot of these regenerative farmers are bringing to the table in terms of proselytizing, evangelizing their neighbors and saying, look, you can do this too. I don't see a whole lot of proprietary, I've got my secret, I'm not going to let anyone else in on it kind of attitude. There's I've been very impressed with the community that's building around that in that world. In terms of time frames, the sooner we can put more carbon in the ground, the better. The sooner we can convert more farms to the style of farming, the better. And I think that there's very real public health reasons to encourage doing it as well, based on the nutritional quality of the food that's likely to be produced. Ann and I are working on a new book now that we're literally just starting that wants to look at that topic, the connection of soil health to human health as modulated through what the way we grow our food does to what's in our food, both our plants and our livestock, and maybe even our wine. And that could put some extra motivation on this. Most of the momentum I see at the moment is bottom up. It's ground up interest among farmers. And that's really what made me optimistic, is that with the economics working out for these kind of techniques, there's growing interest for the simple reason that the farm margins are really tight and farmers are squeezed between higher input costs and depressed crop prices. So the one thing that they have in their control is how much of the inputs they use, their practices. They can't set the price they pay for them, and they can't set the price they get for their harvest, but they can control what they do on their farm. So that sort of connection gave me optimism that these ideas could spread. But even so, there's that classical adoption curve where it's an S curve where very few crazy people start to adopt a change, and then when it turns out they're not so crazy, their neighbors start doing it. There's some people you'll never get to change. I think we're somewhere on the sort of the lower inflection curve. How fast the time frame for transition might be, I don't really know. What kind of things could we do to encourage it? Every farmer I talked to said that if they were paid to put carbon in the ground, their neighbors would probably start doing it faster. That was a very effective, if we actually had some kind of a carbon capture reward system for farmers, that would actually affect things because it's a very clean economic signal. They all stress the importance of demonstration farms and actually showing that these techniques work at scale. It wasn't enough to do it in a small research plot in a university greenhouse. They wanted to see it done on a farm. And they'd rather see it done by farmers than researchers. So I think there's huge opportunities for academic researchers and farmers to work together, devising variants of this new system that would be tailored to different regions. And the other limiting thing, of course, is that you can't just take stuff from Ghana and make it work in Pennsylvania or from the Dakotas and make it work in Ohio. You've got to tailor it. And each of the regions I went to, the principals that I talked to, said that they had made plenty of mistakes along the way, but they'd learned how to do it. They'd sort of tailored a method. And that they could then teach people in their region pretty fast how to make the transition. But if we're taking it into new regions, there might be a lot of new work that needs to be done. And now I've forgotten what your original question was, so. Yes?
Are there any differences between regenerative agriculture and conservation agriculture, or are they pretty much synonyms?
That's a great question. conservation agriculture has been defined by the United Nations as following those three principles of minimal disturbance, keeping the ground covered, and growing a diversity of crops. And they have something else about roots. I think USDA NRCS has added something about keeping living roots in the soil, but I lump that in with keeping green plants. So that's conservation agriculture. Regenerative, I kind of see as this broader label where it's about restoring soil health, which is not crisply defined, but for which it's kind of like our own health. It's not crisply defined, but you sure know it when you lack it, right? And I think soil health is something similar, where you can point to degraded land and go, that's not healthy soil. Even if you can't have a razor-sharp definition of what is healthy soil. There's abstract definitions you can offer in terms of ecosystem functionality and things like that. But I think you have to sort of interpret it in context to be healthy for that region. So regenerative I kind of see as this broader label, which could cover things like reintroducing animal husbandry and cropping. In the formal definition of conservation agriculture, that's not in there. And I was convinced by these farmers that I visited who did not have livestock that you don't need livestock to restore your land. But I was also convinced in viewing farmers who'd used livestock to accelerate the process that you might be able to do it faster if you had livestock. So, and that's a good example of where regenerative has a slightly different meaning. And there's all kinds of arguments now about like the new organic regenerative label the Rodale Institute has rolled out. Well, does that mean that people who are conventional, who go regenerative and become, as I call them, organic-ish, wouldn't be able to use that label? But they may be doing the thing we need farmers to do all around the world. There's lots of arguments about labels, but I think that the really key change in thinking doesn't lie so much in the labels as much as in prioritizing practices that rebuild the health and fertility of the land as the consequence of intensive farming. Because that's the revolution right there. Yes?
Well, one of your very first slides showed rates of soil loss and had the red, the 1.5 versus the blue, which started 0.08 in the no-till. And you had, these are median numbers, and the natural background rate at 0.02 millimeters per recall, and the no-till is median 0.08.
Yep.
And so that's still a 4-time loser on your median.
Oh, yeah.
Right,
Yeah.
so I'm just saying that if you were now to add a slide to your talk, because you do a fantastic job of educating, the general populace about the importance of this. You think it's a great talk. And what if you were to break out that 0.08 loss line, it's 4 times the average median rate. How would you spread that out and say, well, that's the median, and here's how we break even or even get better? How do we build soil? And if you were to build that in your
well, I think
what do you say was a sweet thing?
What I would love to do, because those numbers for no-till, it's for all styles of no-till, right? So it's everything. So what I'd love to do is to get in and find more data now, and look at what do you get for no-till plus cover crops plus crop rotations. Is that the high end of, the low end of those numbers? So you're back down around 0.01, 0.02, or does it make a difference at all? My suspicion is that you could basically get to the point where you've changed the sign and you're building soil rather than even losing it. But I have yet to see that study be done, and I haven't, I did that compilation 10 years ago when I wrote Dirt, and I have not revisited it, in part because there's not a lot of studies that have done all three. And so I went in and I parsed the studies that have looked at sort of erosive effects of no-till and mostly on carbon sequestration from no-till. And what you find is that the no-till practices that sequester the most carbon are the ones that also have cover crops and diverse rotations. And if you only have the no-till and you don't have the others, you're on the low end of the sequestration. My suspicion is the erosion game is similar. But yeah, it'd be a great project for students. Yeah, and seriously, if you wanted something to start with, steal my spreadsheet. But if you add to it, send me a copy.
More questions?
I have one more is, we'll bring it back home. I also appreciate in your talk, you you paralleled the evolution of your thinking and society in your own world, and you showed this garden balloon right in the back of your house. It was interesting, you also showed in the beginning how you stripped the sod. Right?
Oh, yeah.
And I was curious, now that you've learned what you've learned, would you strip the sod again?
Yes, and in fact, what I would do now is I would strip the sod and then I'd rototill the hell out of it. But I would do it once at the start and then walk away from that.
But you wouldn't rototill the sod in. You'd get,
Nope.
you'd get rid of
Well,
all that organic matter.
I would actually think twice. I might basically stockpile the organic matter, compost it, and spread it back on top. But the thing that I would do now that we didn't think to do then is I'd probably just break up that glacial till and do it once. I've had farmers who have like really serious hard pan issues and other things sort of go, well, can I disturb it once or can I disturb it at the start? And I was like, yeah, if you do it and then don't disturb it after that, you've basically reset the system on a better trajectory. So that would be one difference. And if I put a lot of thought into it, I'd probably go, yeah, I'd save the organic matter and compost it. Although, to be honest, we don't really know what the previous owner put in that lawn. So the chief gardener might overrule me.
Right. But as you said, you'd be happy to eat. And I don't have a problem with it either. The farmer who has done greatly reduced glyphosate application in no-till situations, right, a one-time application to say kill off the lawn and maintain all that organic matter on-site, right, as a trade-off issue of building the soil. I mean, this is, I'm asking a very thorny question.
Oh yeah, yeah, and I would, I'd be very tempted to compost it.
But yeah, just ecological subsidies when you bring in organic matter from all over the place. Right?
Well, one of the interesting things about our yard is that in the first couple of years, we were a major net importer. And, in terms of ecological subsidy kind of things, we were putting coffee grounds from Central America all over our yard. Globally, that makes no sense, except, locally, it was down the street. So it was like actually the most proximal best use if you don't take responsibility for drinking the coffee, which I don't. So, if we talk tea, that's a whole different story. But we've now turned our yard into a net exporter. So we now have enough biomass production that we produce more than we need to compost and mulch the yard. So we're subsidizing the city of Seattle's compost operation, which is great. And so you can imagine the idea that, at least in urban settings, if you could do that, you could sort of seed the transformation of one lot and it could spread to others if you were organized about it and used the organic matter wisely. I mean, the amount of organic waste that we produce in cities, without even talking about human waste, which I talk about in the Growing Revolution book, you look at the amount of wasted organic matter from food and yard clippings and lawn stuff, I mean, there's every reason to think we could do a major job of composting urban farms and growing vegetables for cities that way, and doing it with hardly any fertilizer.
Thank you.
Any other questions?
How do you feel about vertical farming?
I get vertigo. I hate heights. But to actually answer your question, my own feeling about it would depend a bit on how it's laid out. There's one of the things that Ann and I are wrestling with now in terms of the nutritional value of foods is what happens between plants grown in soil and hydroponically grown plants. And it looks like a lot of the answer depends on, well, what are you putting in the hydroponic system? At which point, if you can put all the micronutrients and even the mycorrhizal fungi in the hydroponics, are you still missing phytochemicals that the plant would make in response to soil organisms? That's a big question we want to look into. But they also run into energetic questions about where are you getting the micronutrients from? If you're not getting them out of soil, you have to add them. And so are you shipping them from Morocco to actually put in your vertical farm in Seattle or New York, in which case a lot of the case for it being a sort of a wise local thing starts to go sideways. So I kind of like to think of urban farms that are soil-based that using composted organic matter in it would work. So if you have a vertical farm that's actually growing stuff in soil and you're letting light through the sides or something, that could work. I'm a little leery of arguments about hydroponics and vertical farming, frankly, at this point.
Any more? So let's thank Dave.
All right.
Great job.
Thank you.
Great job.
All right.